In recording the geometries of structures, we often find ourselves wanting to figure out the angle between two structures. Those structures could be two lines in 3D space. Here I have a pen and my Apple Pencil, and I have them arranged so that each one has a different trend and a different plunge, and I wonder what is the angle between those two. Well, we could try and measure it with a protractor, but getting the protractor into the right orientation in 3 dimensions is quite a challenge, and if we're dealing with a real rock outcrop, that may be impossible. A similar problem involves planes. So here's my field notebook. If I open it up, the two covers are planes with different strike and dip, and they may have any orientation in 3D space. So if I want to find the angle between these two planes, once again, with my notebook, I could maybe put a protractor on the end here and measure the angle. But on a real rock outcrop, we probably don't have this surface. So we have to find another way to do it. So the way we have adopted is to use something called a stereographic projection. To show how we do this, I'm going to make a sketch as usual on my iPad. And first I'm going to draw a big field. Parallel lines stay parallel, roughly speaking. There we go. And we'll imagine our geologist is standing in the middle of the field, and north is this way. And our geologist wants to measure a geologic structure that is plunging down, let's say, sort of towards us and to the right, plunging down towards the southeast. So let's say the trend of this structure is 1, 2, 3 degrees, and the plunge is, let's say, 37 degrees. So it's coming out towards us and plunging down into the ground. So in order to represent this in what's called a stereographic projection, we need to imagine that our geologist is sitting in the middle of a big sphere. Like a giant bubble. And we'll draw the ground here. There it is. And so this big red arrow will be piercing through the sphere, maybe making a little hole in it, somewhere about there. So now we're going to imagine that our geologist climbs up onto the top of the sphere, and that we make a little tiny hole in the top of the sphere, just here, and our geologist looks down through that hole. So let's see what they see. So when we're looking down through that hole, we're going to see a big green circle, which is, if you like, the equator of our sphere. There it is. And we're going to see that red arrow, and it's going to start in the center of our circle, and it's going to head down this way, 123 degrees from north. Actually, let's bring it around a little bit, and it's going to go out through the sphere about there, and then down here it will head on further down into the ground. So we can represent the location of that point, or that line in 3D space, by measuring around from north 123 degrees. That part is easy. And then we need a way to measure somehow 37 degrees down the inside of the sphere. So in order to do that, we need some kind of a protractor measuring device if we're to make measurements on this plan view of the sphere, which is known as a stereographic projection. And if we can find a way to do this systematically, we could maybe plot 2 lines, or we could find a way to plot planes, and then we can find a way to measure the angles between them. So to show how this is done, I'm going to flip over onto the Visible Geology website, which has a neat stereographic projection tool which helps with visualization. Here I am on the Visible Geology website, and I will click on Visualize. And the place I want to go to this time is quite well buried in the Visible Geology website. I have to click on Explore, and then right down at the bottom, I go to StereoNet, Experimental, tell us what you think. So I think this is quite good. It works pretty well. So let's have a go. There are some instructions that come up when you first fire it up. I think I want to make it bigger so that it occupies my full screen. And you can see that it presents me with a circle and a grid of lines drawn inside the circle. If I click and drag, I can actually turn it around in 3D space, so it looks very much like the bottom half of our imaginary sphere that we had our geologist looking into when we were looking at the iPad. So I can come over here and I can decide I want to add a feature to my sphere. And to keep things simple, at first I'm going to add a line, and let's add the same line that we used on the iPad. One thing is we have to give everything a name in Visible Geology. I'm just going to call this structure A. And now I'm going to come down here and I'm going to put in a trend. And you have the option of either pulling the slider or typing a number, and our number is 1, 2, 3, so I'm going to type 1, 2, 3. You see it's unnecessarily written 0, 1, 2, 3 there. I think I can just trim it back to 1, 2, 3. Now I'm going to tab to the next field, which is the plunge, and in here I'm going to type in 37. And our line was red, so let's have red for the line. There we go. It doesn't seem to be responding to my clicks here. That's looking a little bit better. There we go. Now we have red. Just so that you can see it well on the screen, let's make the line a little bit thicker than the default here. So I click accept. So here we have our line now plunging down in space and coming out the side of that sphere. It doesn't show it extending out beyond the sphere. So now I'm going to go back to my starting location, and I can do that actually quite easily by clicking this little icon up at the top left which says 2D. So at that point I see that I'm back to the start, and I have my grid of lines and I have my little red dot there. So the grid of lines is going to function as a kind of 3D protractor when we do it ourselves, and we do need to be able to do this plotting ourselves rather than relying on Visible Geology to do it for us, because we want to make some calculations and measurements with these points. We don't just want to look at them and say, gee whiz, we plotted the points. We need to be able to do some calculations. So the traditional way to do these calculations was using a sheet of paper with a grid of lines similar to the one that you saw in Visible Geology. So I'm going to flip over now onto the visual presenter, and here you can see what we call a stereographic net, and this is the chart that we are able to use as a three-dimensional protractor in order to make constructions on the stereographic projection. Now, in a traditional class, I would be introducing you to the elements of the stereographic net, which you can see here. The net is, and we will do this on the sheet of paper, but you'll meet them again on screen shortly. So you can see the projection is a circle, and the circle is divided up by a whole lot of lines, some of which have names. The first line that's important is this one right around the outside, which is known as the primitive, or sometimes the perimeter of the stereographic net. These lines that go from top to bottom are lines that divide the original sphere in half in 3 dimensions, and those are known as great circles. And that's a term that's used in geography as well to describe lines on the globe. Then we have these lines here, which do not divide the sphere in half. They're all centered on the top and bottom points, and those are described as small circles. The remaining things to know about on the stereographic net are that there are 4 cardinal points here, and we're going to label those top, left, right, and bottom. Notice that we don't label them north, south, east, and west, because one of the things we're going to have to do is to turn this around to make measurements. So they're not going to be in their standard orientation all the time. But they are connected to the center of the net by straight lines. And there are 4 of these, or 2 if you like to think of them as diameters. We call them the 4 straight radii that go out to the top, left, right, and bottom. So you may be wondering what this is for. So in the traditional method, which I'm happy to show people, we would put our thumbtack through the middle of our net, and we would put a sheet of tracing paper over the top, make a little hole in the center, and then we would do our constructions on a sheet of paper sitting on top of the net, using it underneath as our measuring device. That sometimes gets a little confusing, and one of the challenges for beginners using the stereographic projection is that we're always moving around the tracing paper, which is our real-world projection, and keeping our measuring device still because it's underneath and it's difficult to turn, whereas in the real world, we would ideally do it the other way around. The real world stays still while we move our measuring devices around. Turns out that if we do it digitally using a similar setup, but in PowerPoint, we can avoid that problem and make the process easier. So that will be the next thing that I'm going to show you, is how to set up an equivalent setup and an equivalent arrangement using PowerPoint.